Howdy everyone, welcome back for chapter 13 example problems. In this chapter we're looking at solutions, so it's related to what we did in chapter 4 of Chem 105, but here we're not just looking at molarity and dilution, we're looking at some other forms of concentrations and the math behind them, but also how do we predict which solutions are more likely to be made, how do we discuss different solutions for how much is dissolved in them, for solute versus solvent, and things like that. So when we start off here, we're going to start with what's more likely to dissolve. What solution will probably be made? And the rule that we always have for that is like dissolves like. So this is going to be using a lot of the stuff from chapter 11 with intermolecular forces. If we have two things that are both polar, they're likely to mix. If we have two things that are both non-polar, they're more likely to mix. But if we have a polar and a non-polar, maybe not so much. So it says for each of these pairings, which is more soluble or which is more likely to be soluble in hexane, C6H14. And so the first thing we look at this and say, okay, C6H14, I don't see any FO or Ns, I don't see anything that could be polar. That right there is a non-polar solvent. It's organic. When you see C's and H's, just assume it's organic unless you have a bunch of other stuff. And so when we look then at these pairings, we're going to say, well, which one is also nonpolar? That's going to be the more likely solute. So we look here, we got carbon tetrachloride versus calcium chloride. Carbon tetrachloride, it has polar bonds. C versus Cl is polar, but because it's 4 carbons, and if you draw out the Lewis structure, it's going to be tetrahedral. It's going to cancel out. This is going to be non-polar. I'm just going to put NP for that. Calcium chloride, that's a metal and a non-metal. That's ionic. So there we've gone past polar. We've gone all the way to ionic. Well, that makes it easy. Which one's going to mix with the non-polar hexane? It's going to be the non-polar carbon tetrachloride. Right? Similarly, in part B, we say, okay, we've got C6H6, that's benzene. All we have are C's and H's, nothing special there. That's going to be nonpolar. Versus, I believe this was glycerol with the 3 hydroxyl groups. So yeah, lots of C's and H's. That part's going to be nonpolar. But I see an OH group here. That's going to be a polar bond. It's going to even have hydrogen bonding. It's more polar and hydrogen bonding here, more polar and hydrogen bonding there. So because of that, this is going to be a very polar substance, or at least be able to be very polar and have hydrogen bonding. So again, when we see what matches up with our solvent, it's the nonpolar benzene. Oh, I don't know what I've done. How do we reset this? There we go. It is likely to be the nonpolar benzene that is ending up dissolving in the hexane. Now for the third one, it's a little bit tricky because we see here, we've got COOH. And we talked about that in previous chapters. That's a carboxylic acid. It's going to be polar. It's going to have some hydrogen bonding. And this one has a COOH. It's going to be an acid. It's going to have some polar. It's going to have some hydrogen bonding. So we got to say, okay, that part's equal. Well, that actually makes it easier. Now we just have to compare what's the other part. So here in the second one, this is acetic acid, vinegar. It just has a methyl group, CH3. But this one has that same methyl group and then 6 more, right? That's the key, 6 more CH2s. So it's 1 extra carbon and hydrogen group versus 7 non-polar carbon hydrogen groups. And so when we look at that, this one's only 1, this one's got a lot more non-polar character. That is why this first one, I believe it was the octanoic acid, is much more likely to be soluble in hexane because of all these CHs. So sometimes you got to watch out for that where you say, hey, it's got a polar thing, but it's not the only part of the molecule. You got to look at the entire molecule. In this case, all this nonpolar stuff is going to make a difference compared to just that little bit of nonpolar stuff. All right, for our next one then, now we're going to talk about some of the different ways to talk about concentrations of the solutions, the different mixtures, where we have this one mixture, 14.6 grams of methanol that's dissolved in 184 grams of water. And we want to calculate the mole fraction of methanol, the mass percent of methanol, and the molality of methanol. Make sure you check the spelling, molality, not molarity. All right, so for mole fraction, well, that means we need to get moles of both of these. So for the methanol, we have 14.6 grams of CH3OH. We'll do our one-step conversion to convert that to moles. So grams of CH3OH, 1 mole of CH3OH. Molar mass here, we have 12 plus 3 is 15, 31. It's 32.05 if you're using 2 decimal points from your periodic table. And we'll punch that in real quick. 14.6 divided by 32.05. And we get, what is that, 0.456 moles of methanol. We're going to do the same thing for water. I'll do it up here to save space. So 184 grams of water. 1 mole of water is 18.02 grams. So we'll divide that. And here we get 10.2 moles of water. And then to get mole fraction, we just divide them. We say, what is your moles if you're looking for? Divide it by the total moles. So we do want to watch out for that. So our total moles, we'll take the 10.2 and we'll add the 0.456. And so we are at, let's see, total 0.456 moles of methanol divided by 10 point, what is that? We'll do 6, well, it's 666. I mean, officially we would end at the first one, but just for rounding, we'll keep the whole thing. Moles total. And when we do that, 0.456 divided by 10.666, we get a mole fraction of 0.0428 for the methanol. So that would be our chi for methanol, but yeah. But that's our answer, 0.0428. So it's about 4.28% methanol by moles, but that for mole fraction you leave it in decimal form. All right, for mass percent it's easier. There it's just the mass of the methanol divided by the total mass. So we'll just do that, mass of the CH3OH divided by the total mass. So here we have 14.6 grams. Our total mass, what would that be? 198.6 grams total. So 14.6 divided by 198.6, and then times 100. So this is 0.0735. So that would be 7.35% methanol. So that's that one. Just remember, for both mole fraction and mass percent, it's got to be divided by the total, whether it's the total moles or the total grams. Make sure it's divided by the total. All right, molality. This one is that molality is equal to the moles of the solute divided by the kilograms of just the solvent. This is the key difference. It's not liters of solution like molarity was. It's kilograms of just the solvent. Makes a key difference there. So in this case, our moles of solute, well, hey, we solved that up here in part A. That's convenient. We have 0.456 moles of methanol. Should have boxed that answer and make it clearer. Divided by the kilograms. So, this is grams. We divide by 1,000. 0.184 kilograms of water. And so that means 0.456 divided by 0.184. This is a 2. With rounding 48 molal solution. Okay, so that's how you do those. So just new ways of getting concentrations. They all have their own different number. They have their different uses depending on what you're looking for. Mole fraction is important when you're looking at changes to boiling points based on a mixture. Mass percent, actually we did mass percent I think back in chapter 3, but that was for solids, but similar thing here. And then molality, that's going to be important for the colligative properties, and we'll get to an example of that right next here, about how much does the boiling point change, how much does the freezing point change, what's the osmotic pressure going to be. A lot of them depend on molality. All right, so let's do that one with colligative properties. Freezing point depression. This is why we put salt down in the winter, because we're lowering the freezing point so that we don't have ice on the roads, we have water on the roads. So we're going to do two problems from, or two parts of 13.75, where we figure that out. We want to know what will the freezing point be if we have a 0.22 molal, I can't remember if this was, I think that was glycerin again, in ethanol. We have our normal freezing point and our constant for ethanol, and then we'll do the same thing for salt in water. Same thing, we have our normal freezing point and our constant. Well, the key is that we know that the change in temperature is going to be equal to, they say I, which is the number of particles, times the freezing point constant, depression constant, times the molality. And so we look at that and we say, okay, in this case, this is a covalent compound. When it dissolves into the ethanol, it's going to be one compound still, so I equals 1. We then multiply it by the change, or the constant, sorry, so it's 1.99 degrees Celsius per molal. And then we multiply it by what is the molality. So in this case, 0.22 molal. Molals cancel out. And so we'll get 1.99 times 0.22. And so this is a change of 0.44 degrees Celsius. Now the key thing for freezing point, it's always freezing point depression. The freezing point always gets lower. If we were doing boiling point, it's boiling point elevation. The temperature always gets higher. So in this case, we want to get 0.44 degrees lower than this. So it's negative 114.6 minus 0.44. So 114.6 minus 0.44. Sorry, calculator screen's acting up again. We get negative 115 with rounding 0. Sorry, I don't know why that decimal point was there. Degrees Celsius. That will be the new freezing point. So only a little bit lower. And it's already really cold, but that's how much it would be if it was a 0.22 molal solution. All right, in part C then, we have a 1.50 gram sodium chloride solution in 0.250 kilograms of water. So first off, we have to find the molality. We don't know it yet, we got to find it. So we got to turn grams to moles. So 1.50 grams of sodium chloride, 1 mole of sodium chloride. I happen to know it's 58.44 grams of sodium chloride. So 1.5 divided by 58.44, 0.257 moles. Now we got to punch that in for molality, so 0.0257 moles divided by 0.250 kilograms, so divided by 0.250, and we get this is a 0.103 molal solution. All right, so now we got that molality. We can use that in our equation. So our delta T this time, well now here's a little different. For the I, for how many particles are we going to have, that's an ionic compound. It's a strong electrolyte. When sodium chloride dissolves in water, it completely separates. So when this dissolves, we're going to have sodium ions and we're going to have chloride ions. There's going to be 2 particles in the water for every one of the compound that dissolves. So in this case, I is equal to 2. So this is where for ionic compounds, you got to look at the formula carefully and say, well, how many ions are there really when it splits up? So it's 2. Now times Kf, 1.86 degrees Celsius per molal, times our molality, 0.103. Molals cross out. Our delta T will now equal 2 times 1.86 times 0.103. And so it's going to be 0.383 degrees Celsius. And so then when we plug that in to say, okay, what's it going to be? Well, we start at 0.0 degrees Celsius. We will subtract off 0.383 degrees Celsius. And so that's just going to be 0.383. Negative, with sig figs, we're only allowed 1 decimal point, negative 0.4 degrees Celsius. So that's not going to change the freezing point much, but it's something. But notice when they put down salt on the roads, they put down a heck of a lot of salt. So it's a lot higher molality when this stuff gets going. All right, so that's how you do that. Again, if it's boiling point elevation, then the change always makes the temperature higher. If it's something else, just always keep an eye on that I. If it's in the equation, if it matters how many particles are in solution, well then it matters, is it ionic? How many ions are going to dissolve or split up when it dissolves? So keep an eye on that. All right, that's it for chapter 13. Hope this was helpful, and I'll see you guys back for chapter 14, kinetics. See you soon.